There you are. Okay, good morning, everybody. And also hello to everybody remotely in all kind of time zones. This is the MAPRG session at IETF 118. My name is Mia Kühlewind. I'm sharing this together with Dave Blanca. Dave?
Morning, folks.
Okay, let's move to the next slide and get started. This is the Node Well. This is an IETF session, but we still have a Node Well. We follow effectively the same intellectual property rights as in the IETF. Next. This session is recorded and I think even live streamed, so please be aware of that if you go to the mic or want to say something. And also very important, we also have privacy conduct and a code of conduct, so please make sure you're familiar with that and you follow it, you be nice to each other, and we have a very interesting and nice session and discussion here. Also, something to keep in mind is that this is an IETF session, a research group session, and not a standardization session in the IETF, so there are a couple of differences. In case of MAPRG, what we do today is mainly have some very interesting research presentations and a little bit of discussion about this. This slide is mainly giving you all the links to all the information you need. We have a mailing list. Please also sign up to the mailing list. Feel free to use it also for any kind of information sharing question. There's not much activity, but feel free to do that. And if you're remotely, please use MeetEcho. And if you're in the room, please also use MeetEcho to sign in. So we have some numbers about how many people are here so we can get the right room next time and we can follow the process. Please sign into MeetEcho. And we also use MeetEcho for the queue, of course. Again, this session is recorded. Please be aware of that. And hopefully you know by now how to use MeetEcho to join the queue. And then I have two quick slides here, and that is very hard to read, but it's mainly for you to look up in the proceedings. The IMC, the Internet Measurement Conference, was just 2 weeks ago. And as always, they have a lot of interesting papers. And this time in particular, they had a lot of papers that were looking at IETF protocols. We did actually invite some of them. So you find some from some IMC talks, which are not on the slide set because they are invited today and give a talk. But I also encourage you to look at the slides or the proceedings of the IMC and look at those talks because and papers, they are a really interesting one. For example, about quick congestion control. That talk also was yesterday in the CC working group in transport. There's something about mail, there's about security, and on the next slide, I think there's more stuff about DNS for sure, and BGP, and all kinds of things. So please have a look, it's very interesting. And that's already my intro part. We have a very full agenda today. And that means we will start right away with the first presentation. And Roland, you can come up here.
For the presentation slides. Yeah, hi, my name is Roland.
Yes.
So I'm presenting work of colleagues. So I wasn't involved in that work. I'm just a proxy.
I think you have to select it.
Oh, I have to select it. Okay. Where is it? That one. Share.
Perfect.
There it is. Okay. So this is actually work from Michael, Oliver, and Martina. And I'm just the presenter, as I said. So I try to do my best to answer any questions afterwards. So Quick was standardized, but it also said that it's meant to be a general purpose transport protocol, not just for, let's say, transferring web content, right? And so Michael actually tried to use the flexibility of Quick in order to do some experiments with different congestion control algorithms. And he found out that actually while using it in a 10 gig per second test bed, the throughput performance was actually quite poor in that sense that one of the implementations only delivered 200 megabits per second, which is down there below on that graph on the right hand side. So there is related work looking at quick throughput, and I mean there's a reason for the industry to use quick, so it has advantages, right? But primarily this work focused on the latency and flow completion times, and only a few other prior work looked at the sustained throughputs in high bandwidth environments. Okay, so the testbed setup is very simple. We have a sender, we have a receiver, all Linux boxes, all the same configuration, and there's a software switch which is able to emulate delay, bandwidth, and loss. So that's a very simple, basic setup. And so this is not about real-world measurements out there. It's a lab experiment, more or less. Yeah, so what was evaluated, Michael chose to have 6 implementations because they come with their perf clients. So they have a traffic generator on board, which can be used. And the assumption was that implementers know best how to interact with their own implementation, right? And so for comparison, TCP and UDP was used as benchmark, so to say, using iPerf3 and NetPerf. And no matter whether TCP or Quick Cubic was used as congestion control algorithms. So the baseline is UDP here, and as you can see, it's able to more or less saturate the link, so that's what you can expect to get through. So that is fine. TCP is also more or less able to saturate the link. That's also nothing unusual. So this is showing the average throughput of a single flow, right? But the average just over 10 runs, each for 30 seconds. And now Quick. At least the implementations that were under test showed a performance difference here. So the fastest implementation was Quinn, showing some performance gap compared to TCP actually, 8.22 gigabit per second, while the others are quite lower. You can see that, for example, the move fast is around 2.4 gigabit per second. So yeah, there's more or less huge performance gap, right? So UDP as baseline shows that there's no bottleneck in the sense in the UDP data path. I mean, since Quick uses UDP, that's important. But as you can see, TCP still outperforms Quick to a large extent, and even the fastest Quick implementation cannot cope with the available bandwidth in that sense. So, and TCP performance is also limited by this 10 gig testbed, since we did measurements also with 100 gig per second, and there was, it was possible for a single flow to get up to 40 gigabit per second, roughly. So this is not the end for TCP performance, actually. So what are potential reasons for the limited throughput that we've seen for Quick? For example, MS Quick seems to use only a single core, which may be then here the limiting factor. While other implementations use multiple cores, but this was not shown in the previous slide, but we've seen that the switching the cores actually degrades throughput. So when there's some switching between the cores, there's just a small degradation in the throughput. Yeah. So one factor may be inefficient usage of CPU resources. So if your implementation is not able to use multiple threads or cores at the same time, this may be one reason for limited throughput. So since we are, Michael, only compared to TCP, not to TCP with TLS, so the question is whether it's a crypto that is here limiting. But that doesn't seem to be the case. So at least two implementations of the set that were looked at, you were able to disable the crypto. And as you can see here, for comparison, the throughput is not that much lower in case you're using the crypto, which is the default, right? And if you're turning the crypto off. So this is not explainable by the crypto. What we've seen is also that in comparison to earlier work, the throughput has been tremendously improved by large factors like 5 or 7 times for certain implementations, and even while asking the implementers of one implementation, they got up from, let's say, 200 megabit per second to at least 2 gigabit per second. That was, in that sense, also some kind of improvement. Yeah, other things that were looked at is, for example, packet loss. So how do the quick implementations react to packet loss? As you can see, for comparison, the black line above is basically TCP. We have very low packet loss ratios here, like 0.05% actually. And as you can see, all the quick implementations basically are limited in their throughput by seeing packet loss. In comparison, TCP doesn't have that degradation in throughput. Also, packet reordering. On the right-hand side, you can see that some implementations probably misinterpret reordered packets as losses because it was ensured that, let's say, that the feedback is fast enough there, so there are no timeouts. And in that case, you can see that, yeah, several implementations have problems seeing packet reordering. So, yeah, as a conclusion, more or less, the current quick implementations, at least the ones we looked at, are not at the same level as the TCP implementations. And it's not only the crypto, it's probably also how it's internally implemented, in the sense that is it possible to use multiple cores and so on. So, okay.
I'm sorry, it was my fault.
So I guess my time's up. Okay, that's basically all I have to say. I mean, we didn't study in-depth or did some in-depth analysis for the reasons, as I said, but that's difficult, yeah, to say. So maybe it's also offloading. I mean, probably with Quick, you have more interactions between user land and kernel. While you can use more optimized implementations with the TCP stack inside the kernel. As I said, that's all for sustained throughputs. It's not for getting the web content, which is oftentimes faster with Quick. That's all I have.
Thank you. Yeah, we have some quick questions in the queue while I try to fix the slides. So please continue.
Michael Tüxen, you're suggesting to use multiple cores for processing the stuff. For TCP, did the TCP case use multiple cores? I mean, you use a single TCP connection, right?
Right, right.
So that goes on a single core.
Yeah, I think so, yeah.
Okay, thank you.
Hi, I'm Alan Frendel from Meta, I'm one of the contributors to Move Fast. Thank you so much for bringing this work. I think it definitely highlighted to our team that we have not done a good job of instructing people on how to performance test, and I don't think our defaults are representative of how well our implementation can do, and there's a lot of nuance to tuning Quick. But
Okay.
Thank you again for bringing this work, and it shows that we have some work to do. Thanks.
Yeah, thanks. Yeah, so we all thought that it's probably exactly that thing that you need to have some deep knowledge how to do it very efficiently with the perf clients, right? And so, yeah, you need some guidance there.
Yeah, thank you so much. And we have another talk actually also looking at quick performance of stacks. So let's take that talk and maybe we have some more questions afterwards. Thank you, Roland.
There are
CEO's
more
coming up.
questions in the queue.
Yes, I'm sorry, but let's have the talk and then you can resume to your question because it's also about performance. I didn't, no, let's use this, so you have to tell me the next slide. Or you can do it with your phone. Just say next slide.
All right, so the last talk was a perfect segue and setup for my talk. My talk is basically also looking at quick performance. Next slide. We can skip the slide. Next slide. Okay, so Quick is amazing. Is it amazing? We don't know. We know that Quick is a user-space implementation. It has faster connection startup and a lot of different benefits. I think the one that is not under dispute is how much benefit you get from faster connection startup. The other potential attributes of Quick, it's not clear how much they actually contribute to either making things better in terms of speed or throughput. And one of the things we started out to do is basically understand when is Quick better than TCP? When is H3 better than H2? And I think one of the things that motivated us is this debate where you look online and you'll notice that there are different benchmark numbers about when is one better than the other. And from the last talk, we already saw that even trying to do controlled experiments is challenging because you actually need to be able to get the right parameters, do the right set of tuning to get something in a controlled environment that reflects what is out there in production. So that's the backdrop for our study, trying to understand why is one faster than another, but more importantly, understanding under what conditions do you actually get to see these speedups. Next slide. So as Alan had mentioned, just getting source code is not enough. You actually need a bunch of optimizations and a bunch of tuning. And when you start to look online, you will basically realize that trying to get your quick stack to be performant requires these optimizations, special configs, a bunch of code. And I wanted to thank a bunch of the people in the IETF quick working group that work with my students to try and help us tune things. We realized very, very quickly that it's not that easy to tune our servers to be just as performant as Meta servers. So we gave up on trying to do kind of testing from our local development setup. And so we decided, can we test what exists online? And the challenge there is if you're trying to test and compare Google's implementation of Quick versus Meta versus Cloudflare, their production implementations, you don't really understand why you're experiencing what you're experiencing. You don't understand what aspect of the performance is due to optimizations, what aspect is due to config, what aspect is due to their code, because a lot of this is just a black box that you're observing from external. Next slide. And so a lot of what we ended up doing is we basically try to take a fuzzing approach to this. So we don't know exactly what they're doing. But we can try and play around with different kinds of clients, different kinds of network conditions, different kind of object sizes. Basically, we can try and fuzz the different types of interactions that you can have with their servers. And then we can create queries over the packet traces, the dumps that we get, try and reason about why one is getting better throughput, why one is getting better performance than another. So my student, Alex, created this really amazing framework that would basically spin up different types of clients, different quick clients, so a Chrome client, a Move Fast client, NGTCP client would use network emulator TC to basically play around with the network conditions so we could like emulate different loss conditions, emulate different bandwidth, and then essentially we work with the IETF to basically get different endpoints of objects of different sizes from several of these companies. And we basically played around with their servers and essentially downloaded downloaded objects from the servers multiple times and created a large database of packet traces, which we then analyzed to look at how did the congestion window evolve, when different types of packet losses happen, or when latency changed, how did the protocol react. So when we're looking at this, we're not just looking at Quick as a whole, we're also trying to look at its internal congestion control algorithm. We're trying to also look at its different handshakes and trying to understand how all of these are essentially interacting. So I know I don't have a lot of time, so I was trying to make this very short. We have a paper online somewhere, and we have a bunch of different insights from the study. I think the kind of very obvious one is, yes, when you bring down the handshake cost, life is amazing, but it turns out if you have really large objects, then the handshake is actually very marginal. So you get a benefit from a faster connection establishment, but this is not that noticeable when you have large objects. And so you can get fast startup, but if you're like doing things that require bulk or large transfers, this is not where most of your benefit would be coming from. Another thing we observed was, you look at the implementations of TLS at the client and server, and on some notion, you probably expect it to be the same suite of protocols, but it's not exactly the same suite of protocols that were on all of the clients and the servers. And this actually created some performance overhead. So certain clients had some expectations on what the server would do, and when the server did not behave in that way, then this basically led to a different set of handshake protocols that made it faster, that made it slower to essentially set up the connection. There were some issues with congestion control, which I'll briefly talk about. And then head of line blocking, I think there is a lot of potential there, but it requires a lot of configuration. And when we were doing the study, we didn't observe a lot of the complexities required to actually realize this where it being implemented. Okay, we have a bunch of these. I feel like everyone that studies and compares Quick has these like arbitrary heat map style figures. So we have a bunch of these in the paper, and in all of these figures, you'll notice that at the very bottom, it's basically a combination
You have to take the mic with you.
All right, at the very bottom, it's a combination of the provider and object size. You look at this axis, and it's basically what aspect of network we're changing. So object size for different providers, and then here we're changing the latency. We have other latencies we play around with, but there's only so much you can show in a slide. At the top, we're changing loss rates. And the blue boxes are basically where H3 is amazing. The red boxes are basically where H2 is amazing, where amazing here is just faster. And all of these figures are basically for a single object. We have figures in the paper for multiple objects also. Next slide. Okay, so, sorry.
Go ahead.
So I wanted to focus on one thing here. There are more details in the paper that focus on every box. But looking at two boxes here, some company called Google, never heard of it. Some company called Facebook, don't think they exist anymore. You'll notice that if you look at their kind of packet spacing, which is a lot of what we did when we're analyzing the differences, is basically looking at the packet spacing and trying to intuit why from the packet spacing the protocol is behaving differently. And in this scenario, what we're trying to intuit is basically aspects and properties of the congestion control. So I think what I want to kind of highlight here is, while this conversation here is largely about QUIC versus TCP, in reality, what we're really talking about here is what congestion control algorithm is being used and how correct is this implementation. And I think this is something that we gloss over a lot when we compare QUIC with TCP, is that TCP is not a monolith. TCP is a lot of congestion control algorithms. And TCP has these algorithms from the kernel, which means they've been tested over and over and over. And if you look back enough, they all had bugs. QUIC, when we did the study during the pandemic, a lot of these protocols were new, bugs were being fixed. So I think there's a bit of unfairness when we just say QUIC versus TCP. We need to basically say what version of QUIC, what actual congestion control protocol, what configuration of that protocol. And these are subtleties that we, as the researchers, highly overlook. And I am also to blame for overlooking much of this. But I don't have that much time to talk about my issues. So here we're looking at differences between two providers. And one of the things we start to notice is that these are both using BBR, and we can go into details later about how we try to figure out which exact algorithm are being used. And one of the things we noticed in one of the providers is that they had a subtle bug in their implementation, and that is essentially what leads to lower performance. We spoke to the amazing developers from that random company. They fixed the bug. And presto, it improved performance a lot. Next slide. I'm probably running out of time now. Yes. Okay. Yeah. So. Oh, sorry. Okay. Well, so I think my main message here was that just comparing QUIC and TCP without going into the underneath congestion control or the configurations hides a lot of the subtleties. What I'm trying to do now is redo our paper, but as an automated service, and I'm trying to focus now on bugs and trying to find bugs. And I was trying to get more people to work with us. I think the reason why this worked out so well last time is a lot of the QUIC working group actually helped us set up endpoints on their servers. They answered a lot of questions when we tried to set up our own servers. And I think here we're trying to get not just engagement from the QUIC working group, but also from researchers, because we're trying to find ways to model various transport protocols and create much richer fuzzers to essentially expose different bugs. And with that, I will yield.
Thank you. Yes, stay here for any kind of questions, because we did reopen the queue again. Jeff, you're next, but if you want to jump in the queue for this talk, please do now. But I already want to thank both of the speakers for the work. I think it's very interesting, and I hope you come back with more results later.
So my question, Jeff Houston, is for the first presenter.
Yeah.
So
And Roland, you just can grab a mic, right?
So let me then ask it. I've noticed in performance measurement that TCP line card segmentation offload has a dramatic impact on the throughput you actually get, because you send off this humongous packet into the line card, and then the line card basically offloads all the rest of the work. With QUIC, that's not possible. So the real question is, in your measurements, was that line card segmentation enabled or disabled? Did you actually go to the effort of turning all that off?
As far as I know, the offloading was enabled, and there were also done some measurements about the impact, and that the impact wasn't that huge, actually.
We've certainly found it's large when you're getting a high packet load. So when you're on very, very short latency and you have 2 to 3 milliseconds, so you're frobbing the packets really quickly, the per packet processing does become interesting on the line cards. It's just a load you're getting rid of that QUIC is unable to do so. It's pushing it back into the CPU and the interrupt structure. So it's certainly an area, I think, of a little bit more discussion and measurement. Thank you.
Yeah. So we did experiments at 100 gig per second where this is even more important. And so we are well aware of all the optimizations that might be there.
Hi, Brian Trammell. Sorry, I'm a little bit late. Excellent talk, both of you. Thank you very much for them. Theo, I've already sent you a message asking if I can borrow your slides for a lecture at ETH in a couple of weeks. There's something that came out of both of these talks I think is super interesting, and I'd like to encourage the whole community to keep looking at things, because like we're looking right now at a very early stage in the performance measurement. If you look back at some of like I forget what they were called, but some of the projects to like get TCP up to 1 gig, up to 10, TCP up to first 100 meg, 1 gig, 10 gig, et cetera, et cetera. I think it'd be really interesting to do a longitudinal study where we can sort of compare how fast did TCP get faster versus how fast is quick getting faster. So like, you know, I think we did a lot of like quick uptake measurement in MAPRG like a long time ago, and everyone's still citing those numbers because they're kind of boring. I'd like to point out that this work will not get boring that fast. So thank you very much to all of you for doing this.
Thank you.
Okay, thank you very much. And we have one more quick presentation. You can come up, please. Are you still requesting sharing? Yes, you do. Sorry.
Okay, so hi everyone. I'm Mike Kunze from Aachen University, and this will actually be a two-part talk. So Konstantin will be joining me later on, and we hope that handing over control will work properly. So this is work also on the real use world of Quick. So we've done a large-scale web measurement to assess the use of the spin bit and of ECN with Quick. And the second part is also part of our collaboration with TU Munich. And yeah. Okay, so short overview of our methodology. So we've done large-scale web measurements from our vantage point in Aachen. We have essentially fed in a few top lists as well as top-level domains. I've tried to resolve them. So just a quick overview here. Have tried to establish quick connections then, or identify which hosts support quick. And then finally, we've then of those connections where we had quick connections, analyzed the use of ECN and of the spin bit. And I will be presenting the results for spin bit, and Konstantin will then take over for the ECN use results. So the spin bit, just a rough overview. It's a mechanism that enables RTT measurements. It's quite simple. So the client always spins the bit and the server just mirrors the bit, and this enables the RTT measurements. And yeah, while it is a nice mechanism, it's only optional and only few publicly available SECs support it. And hence we were interested in finding out how often it is used in the wild. Second, even though if hosts want to enable the bit, they are mandated to disable it sometimes, to also allow hosts to decide to not use it and don't face any disadvantages in the wild. And there are different ways for disabling the bit. And hence we were interested in finding out how the bit is then used in the wild. So for example, if this mandate is used or not. And then finally, even though people could use the bit, the usefulness of it in the wild is unknown. So there have been a few tests and test settings like the one Roland presented, so in just lab settings. And we were interested in finding out how it's actually useful in the wild. And the bit or the mechanism also includes application delay. So for example, if the client waits until sending out a flipped version of the bit, so to trigger the measurement, then this could delay the measurements. And the bit is also vulnerable to reordering. So if we take a look at the bit up there and just reorder it with the packet in front, then we'll suddenly have 3 measurements instead of 1, and 2 of those will produce a very short RTT. And thus the final part of our measurements of our study was to find out how accurate the measurements are in the wild. And today I will only focus on the first and the third questions. For the second one, I refer you to our paper. So regarding the usage of the bit in the wild. So you can see here now our results for IPv4, but the results for IPv6 are in general similar. So of the around 500,000 quick domains, so the 500,000 top list domains that support quick, we see that 6.9% of them also support the spin bit, while for the .com, .net, and .org domains, we see that 11.1% of the domains supporting quick also support the spin bit. So in general, the spin bit sees use in the wild. However, we were then interested in also looking at the underlying host support, and there we saw that this percentage difference is even more pronounced. So we can see that almost half of the hosts providing the .com, .net, and .org domains also support Spinbit, while the percentage is much smaller for the top lists. And as we kind of thought that there might be some impact or some impact regarding the providers providing those domains, and hence also looked at who's actually using those or providing those domains using chaos AS2org resolution tool. We then deciphered that and found that the top two providers of the quick connections, that those don't or only barely use the Spinbit. Then if we go further down the list of providers, so you can see the absolute numbers in the second column. So already quite smaller numbers of connections, but here we can see that there is a sustained use of the Spinbit of more than 50% of their connections. And also for all the other remaining connections, we also see a Spinbit use of around 50%. So what we gather here is that the Spinbit, in contrast to the general trend for quick, which is largely driven by the large providers, that the Spinbit is more driven by the small to medium providers. And with that, I would like to continue with the RTT measurement accuracy. And for this, we basically used all the connections that showed some Spinbit activity, so where we saw some spinning, and here we compared the RTTs that were produced by the Spinbit with the ground truth that the quick stack estimated. And we further compared the results for the received packet order, so basically what the network operator would see, and we then also used the sorted, or we further sorted the packets by their packet numbers to assess the impact of reordering, or rather for that, or in that sense, filter out the impact of reordering. On the right-hand side, you can now see the cases where the Spinbit RTT was larger, so where we saw an overestimation. On the left-hand side, it's an underestimation of the Spinbit, and in general, due to the mechanism, for example, the application delay included, we would expect to see more values on the right-hand side. And this indeed showed true, so we saw quite a lot of overestimation, and in particular, the bar on the right-hand side, or rightmost side, with more than 200 milliseconds of overestimation for quite a lot of connections. Interestingly, however, we also see some underestimation where we're not really sure why that happens. So that definitely deserves a little bit more attention in the future. However, those are now only absolute numbers, and we also had to look at the relative impact of those results to see how the accuracy really matters in practice. And for that, we also, you can now see here on the right-hand side, again, the cases where the Spinbit RTT is larger, on the left-hand side where it's where the real RTT is larger, and we can see that for around 30% of connections, there's only around 25% difference in the RTTs. So that's quite nice. However, again, we see on the right-hand side quite a lot of cases with large overestimations, which I believe might not be that great. However, I'm not a network operator, and hence I don't know how useful this is really in practice. So that would be something that we're really interested in finding out, how useful those measurements really are. With that, I'm now at the end of this first part. So just two takeaways here. You can start trying to hand over control. And what we can gather is that the Spinbit indeed is used in the wild, and that the RTT measurements are kind of an ambiguous picture. So they are often quite accurate. However, there are also often large overestimations, and there's also underestimation, which we didn't expect. And so this is really something that we intend to look into more in the future. And now Konstantin will take over with the second part, I hope.
Yes, as Ike said, we also looked into the usage of ECN. Small recap is that with ECN, basically in transport connections, receivers need to mirror back the ECN's information to the sender. And this ECN mirroring has been optional before with TCP and is now a must in the quick RFC if these ECN signals are accessible by the quick stacks. But there's also a little ambiguity in the RFC, which says that some quick stacks can also not, or can choose to not implement it. And so we asked ourselves whether now ECN with quick can be used. And for this, we again visited websites via HTTP3 and quick, and then logged the ECN counters. And for the top list, we found that 3.3% of the quick domains supported ECN, and for the ComNet.org domains, we found that 5.6% supported this. So given that mirroring should actually be mandatory, we see a quite low support. And when looking into the servers that provide these domains, we found mainly the Lightspeed HTTP3 server, Amazon CloudFront CDN, and some tossed by Google, which mirrored ECN. So again, we found a low support by hyperscalers and content providers, and this could be due to two facts. On the one hand, the quick stacks could simply ignore ECN, or the network might interfere. So it could happen that routers simply take ECN signals like ECT0 and replace it by not ECT. So then we not get any ECN mirroring information from the quick stacks back. And to check for this, we then employed some traceblock tracing to see if the path basically changes ECN. And what we found is that there's no visible ECN clearing for 97% of the domains. So for 2% of the domains, we saw some visible clearing. And this has been mainly been impacted by tier 1 ISPs. So 98.6% of the domains that showed clearing were affected by this one ISP. And this affected especially smaller hosters, and especially after we saw route changes in December 2022. However, for the content providers, we saw that the missing support cannot be ruled out due to clearing. So we saw that these content providers support ECN via TCP. So either the quick stacks or undiscovered middle boxes ignore ECN. And when looking into the quick stacks of these different providers, so the open source stacks that they are using, indeed, many are lacking ECN support. Okay, so now we saw that some domains are mirroring ECN, but this is only half of the story, because to then also use ECN with quick requires an ECN validation approach. And this checks whether the first packet shows some timeouts, for example, due to ECN black holing, or whether the wrong code points are mirrored back, or whether there are undercounted code points. So for example, whether there is some route flapping and some routers are removing ECN code points, or if there are stack issues. And what we found is that only 0.2% of the ComNet.org domains pass this ECN validation approach. So 96% of the mirroring domains fail. And this is mainly due to two facts, due to undercounting or due to remarking. And we found the undercounting for the Google AS and the Lightspeed server. For the Google AS, we are not exactly sure why this is happening. Related work suspects that Google may use some data center TCP internally, and maybe Quick is now leaking this internal ECN information outside of the data center. And for the Lightspeed server, we saw that after packet number space switches, Lightspeed disables ECN sometimes. For the remarking, we again found the tier 1 ISP, which besides clearing ECN also remarks it, so rewrites ECT0 to ECT1, and we again found Google's AS. So all in all, we can say that there are multiple challenges for ECN with Quick. Several quick stacks do not mirror ECN, some networks elements clear signals, and we often see ECN validation to fail due to stack and network impairments. These have been all the results from our main vantage point in Aachen, but we also saw that the usage is limited on a global scale. We never saw more than 0.4% of the domains pass ECN validation, and we saw worse results for IPv6. And these results are also interesting beyond Quick, because they can have a significant impact for another ECN mechanism such as L4S. As I already said, we see this ECT0 to ECT1 remarking. And this can be detrimental for L4S because L4S uses ECT1 now to distinguish between L4S and traditional traffic. But there's also good news, because we see that there's a trend which is probably to be increasing. We see changes over time. When there is this quick RFC around them, there may be rework of stacks to support ECN in a more wide or in a more broad way. And we have open tickets with a stack vendor and are in touch with the ISP for debugging these images. Okay, so all in all, we showed you two large-scale longitudinal quick version measurements. Once on the optimal spin bit, which sees quite broad use in the wild, however shows some measurement accuracy issues. And then we showed you some results on ECN, which is actually mandatory, but significantly limited on a global scale due to many challenges in stack support and faulty network devices. And if you're interested in more details, we have quite plenty more detail. Check out our paper. Thanks.
Thank you. Brian.
Hi, Brian Trammell. I thank you very much I just complained that like we're not looking at Quick in the wild much anymore, and now excellent paper, and this is pretty much with the spin bit and ECN, the perfect nerd site for me. I want to come and talk to you later. I have a lot of things. The one question I want to ask here is on the spin bit sort of overestimation, where you're using ICMP, I might have missed it, you were using ICMP ping as the ground truth for RTT, or?
No, we're basically using the estimations provided by our quick stack. So we're using
on your side. Okay.
We're using, so we essentially used the minimum round trip time estimated by Quick, and then compared that with the spin bit measurements.
Okay, cool. That's really interesting. Let's talk offline. Thank you very much for the work. This is awesome stuff.
And I will lock the queue in a few seconds. Martin.
Thanks for presenting these results. I'm a bit surprised about the spin bit measurement results, because we had a long discussion about the spin bit when we were designing Quick, and there was a lot of work done during the hackathons, and some people evaluated the feasibility of the spin bit to accurately measure the RTT, and the results we got from these groups were basically, yeah, spin bit works great, and you can accurately measure the RTT. So there seems to be like a slight disconnect here between those measurements and yours.
Yeah, if I may, so one idea that I have, I don't know if how exactly those methods were in the hackathon, but what we essentially looked at was the beginning of a connection. So we did those, as I said, in the web measurements, and only requested like the first few bytes of or the first few kilobytes of a file, and hence we might suspect that there would be something in that HTTP stuff in there, so that at the start of a connection, this application delay actually has more of an impact than in an ongoing connection, and this might be something. So I don't know if that was the case in those hackathon
I'm not sure. I was not involved in those measurements. I just wanted to find out it might make sense to sync with those people and see what kind of measurements they did, and if they had like some tricks to get a higher confidence there.
Yeah. So again, or an additional aspect. So as I said, we try to design this study to measure both the spin bit and ECN at the same time. So it's not really focused at the spin bit. And there are, for example, also regarding the second question that I didn't talk about today, also some aspects that might be, that one might could look better at if specifically designing the measurement study for the spin bit.
One more person, Tara.
Hello, thank you, Tara Taraki. I was wondering, just for clarification, because you keep saying that the spin bit is being used, but if I understand correctly, you're measuring domains that have the spin bit enabled, and I'm wondering if that translates into it being actually useful and being used.
Yeah, so we say a domain has the spin bit enabled if it is used. So in essence, we take a look at the bits that we get back in the spin bit field, and if we see at least 1 0 and a 1 1, then we say it might use the spin bit, and we then compute or try to compute the RTT base of it. And if that makes kind of sense, so it's not like in a very, very low millisecond range, then we deem the spin bit to be enabled.
But wouldn't the definition of it being used being used by people who are measuring RTT rather than it being enabled by domains?
So you're talking about if people use it on the way. So we were just looking at the endpoints and trying to find out if the possibility would be there in the network to measure the RTT based on the spin bit.
Okay, thank you.
Thanks.
Thank you. Yes. Actually, I think we have again a problem with the next slides. Or Dave, can you see them? Otherwise, I would actually, sorry, Sushit, I would actually like to ask Marnard to come first. We just switch the order very quickly and fix the slides in the meantime. Thank you.
No worries, thank you.
Interesting. You can also do it this way. Thank you.
Okay. Hi, I'm Maynard from TU Dresden, and today I'm going to talk about transparent DNS forwarders. So transparent DNS forwarders are often misbehaving CPE devices in ISP networks, but how do they work? So let's consider a simple example. We have a client who wants to resolve the domain name, let's say google.com, and he sends its DNS request towards the transparent forwarder. The transparent forwarder then forwards the request to its configured recursive resolver. And at this point, as you can see, the transparent forwarder does not rewrite the source IP address of the DNS request. So the recursive resolver more or less does not know of the existence of the transparent forwarder. It only sees that the request supposedly comes from the client. So it does its resolving job, and as soon as it sends the DNS request, the DNS reply back to the client then gets a reply from an unexpected source. So that's basically how transparent forwarders work. Why should we even care about these devices? First of all, OpenDNS in general enables amplification attacks. So we have an attacker that sends a spoof DNS request, which leads to flooding of the victim with unwanted DNS responses. And we want to lower the impact. So what did we do? We set up our scan campaign to measure the complete ODNS infrastructure. And what you can see is that we find more OpenDNS devices than other campaigns. And why is that? That is because we include transparent forwarders. And we confirmed with controlled experiments that these scanning campaigns do not include transparent forwarders because they do not detect them. And that is a major problem because back in the days, around about 10 years ago, we had about 20 million OpenDNS devices. And that, reduced the amount, decreased rapidly to roughly below 2 million devices. But the amount of transparent forwarders not only remained the same, but it also increased. So the problem is that the transparent forwarders transitioned from an exception to a major part of the ODNS infrastructure, accounting for now around about 31%. Why do they miss these transparent forwarders? It's mostly due to efficiency reasons. Their scans use static queries, and they only evaluate the incoming traffic. That means that many scanning campaigns just consider the replying source IP address, which is the IP address of the recursive resolver and not of the transparent forwarder. So the transparent forwarder remains hidden. Let's have a look at the transparent forwarder deployment. We highlighted in this plot the emerging markets, and as you can see, countries classified as emerging markets are more likely to host more transparent forwarders. And furthermore, we count the different ASs per country, and as you can see, in each country, multiple ASs host transparent forwarders. So it's not an exception to a single AS or something. They are distributed all over the world. And let's have a look at the share of transparent forwarders. So as you can see, compared to other the ODNS components, in some countries, the ODNS consists almost exclusively of transparent forwarders. Yeah, we want to reduce the impact of transparent forwarders. So we set up our own scanning campaign, which includes all ODNS components. And we always try to get in contact with network operators. And yeah, so finally in April 2023, we succeeded with that somehow. A large ISP added filter rules at their resolver, which eliminated 280,000 transparent forwarders at once. So we have a decrease here from 38% of transparent forwarders down to 31%. So there's still a lot of work to do because we want to eliminate, in the best case, all of them. But yeah, this is where we need your help. So if you're maybe a vendor and you think you could be shipping transparent forwarders, please talk to us. We would like to understand your implementations better. So far, we have identified mostly MikroTik and Cisco devices, which are misconfigured by default. Yeah, and on the other side, which will wrap up that talk, if you're unintentionally hosting transparent forwarders, though you think in your network there are transparent forwarders, we have yeah, 3 main points why you should update your deployment. So first of all, of course, these devices facilitate DNS simplification attacks. Furthermore, they allow attackers to exploit anycast deployments, which challenges the POP-based DDoS mitigation. And finally, your AS forwards packets that look like spoof IP packets. So attribution is challenging because these packets are triggered outside your AS. What are the solutions to that problem? First of all, you can update the filter rules at your firewall, or you can update transparent forwarders individually. Yeah, for more details, you can find a paper, which is also linked in the slides. And you can find our weekly scan results where we publish all OpenDNS components under odns.segnow.net. Thank you very much. There's a question.
Yeah, thanks.
Yeah, Lorenzo Calivi, can you go back? We don't ship any forwarders, nor do we run any forwarders, but can you go back to the sort of the slide where the invalid source address is reply arrives at the host? Sort of like, I don't know, slide like 4.
You mean that one?
Yeah, this one. So I'm confused about how this would, yeah. So if it gets a reply from the unexpected source, what I don't understand is like, why would it even take that reply? Because I'm familiar with the Android implementation, and it should reject it because it uses a connected socket and we'll just drop it.
It is rejected, but we can measure that, and we can use these transparent forwarders because we get a valid reply from them.
So what I guess I don't understand is, if the client rejects it, why are people doing this at all? It doesn't do anything. Is it just like literally a mistake, or?
Yeah, it's just, it seems like to be a bug in the DNS implementation. So there is something wrong where the DNS server fails to rewrite the source IP address. So it just gets the DNS request and simply forwards it without any modification to the IP header.
So we've got 3 million of these in the internet.
And no. You get, one second. We have 600,000, yes.
600,000 of these. They do something that doesn't do anything. Okay, I guess I'm surprised. It might be worth like trying to contact some of these and saying, hey, like, why do you do this? Because it doesn't do anything useful. Yeah.
Yeah.
Let's follow up offline, actually. Sorry.
Okay.
But like, we're all here. Let's talk together. Thank you so much.
Thank you very much.
Now we try the online presentation again. Hopefully it works now.
Great. I can see the slides.
Okay, perfect. I will hand it over to you.
Sure.
Now you should have control, right?
Yeah, I think I
Perfect. And we can hear you, we can see you, you can start.
Perfect. Yeah. So, hi everyone. I'm Sadish. I'm a PhD candidate here at the University of Washington, and I'm excited to present some of this work on behalf of all of my collaborators from Northeastern and Cloudflare Research. And today we'll be talking about some of our work on characterizing DNS resolver behavior to DNSSEC queries, and this is an active paper in submission. So over here in this chart, you see that this is from APNIC, and it shows the total percentage of DNS resolvers that are used by clients which are in the same AS as the client, which is shown with the blue line on top, and it also includes users' queries to public open DNS resolvers such as Google DNS, Cloudflare, and which is over here in the orange line and the other little colored lines at the bottom. But what we see here is an increase in the total number of clients which use resolvers that are configured by their ISP. So over 65% of these internet clients use such resolvers. And we also see that there is a decreasing trend over the last 100 days of this data that you see here for people using large public resolvers. But there are new regulations and policies such as the EU resolver policy and others across the world which have filtering requirements for security and legal purposes. And the deployment of managed DNS resolvers helps these network operators comply with these regulations and is possibly the reason why we see an increase in usage and deployment of these resolvers compared to using the larger public ones. So this makes it important for us to understand their behavior, especially around the answers they return, the ability to validate and protect users using these resolvers, and any other metadata they may be sending back to their clients. So while some of these studies were done in the past, none of them specifically focused on the response correctness when DNSSEC queries are made by the client. And as many of you may be aware, the usage of DNSSEC allows resolvers to return cryptographically signed answers for user queries. And these are obtained from the respective name servers, and this guarantees the authenticity of the answer and the integrity, confirming its correctness and validity. But recursive resolvers can also drop signatures in the answer being sent back to the client and only send a part of the answer, forcing the clients to either perform all of these lookups themselves to validate the answer that they have. And this kind of brings us to the core part of the question, the research questions we asked in this effort. First, we want to understand to what extent these recursive DNS resolvers actually provide valid or correct responses to DNSSEC queries. And second, to what extent are recursive DNS resolvers actually validating DNSSEC responses they obtain from their name servers? And a good way to do this would be to analyze the DNS resolvers within each network, but many of these may be configured to be private and are only accessible to clients that are within the same AS to provide DNS resolutions for them. But this would be really complex to do without having a lot of individual probes within each of these networks. So as a sort of approximation, we try to understand the behavior of these resolvers, which are configured to be public. So these are open DNS resolvers and in the IPv4 space. So we ran a ZMAP scan for OpenDNS resolvers querying for google.com's A record, and that resulted in a total of 9.97 million resolver IP addresses, to which we further sent DNSSEC queries for google.com, which returned 7.93 million resolvers. And we also obtained at the same time a 101-day snapshot from Shadow Server, where the total number of unique IP addresses that were observed were 26.97 million. And when we probe them for DNSSEC with DNSSEC queries at a given time, it comes down to 7.3 million resolvers which are available and actually respond. But despite Shadow Server actually finding over 2 million or 2.5 million resolvers in their daily scans, our snapshot finds a lot more, which is almost 7 million resolvers. And it's likely because of the filtering opt-outs maybe that Shadow Server is respecting because they may have received those requests from operators. But we observed in these responses that over 98% of these resolvers actually return successful responses to the clients that are making these queries. And especially when the queries were set with where the DNSSEC bit of the query was set. And there are a very small number of them that return error codes. But unfortunately, not all successful responses that we received when we analyzed were actually correct, and which means they did not have the correct IP addresses that belonged to Google's advertised IP ranges. But interestingly, there seem to be resolvers out there which aggregate the results from multiple name servers and provide all the list of results that they may have obtained, returning over 10 IP addresses in the answer for the query. But all of these answers are fully valid, which you can see in the blue box to the right. But a majority of these resolvers actually return one IP address in the response. And over 95% of these responses are actually invalid and do not belong to Google's advertised IP range. But this result was quite interesting. So we analyzed this further and realized that 99% of all invalid answers that we see actually include one of these 4 IP addresses in their answers. And interestingly, these IP addresses are advertised by different networks like Level 3, Deutsche Telekom, Korea Telecom, and Fastweb. But these IP addresses also, however, match the fingerprint from previous DNS censorship measurement studies that were done about the Great Firewall and their abilities. So we also observed when looking through census for the certificate scans that these IP addresses were present in the common name field for a lot of certificates, and all these certificates are invalid. But these certificates were found in devices such as Fritzbox and also in some cluster management tools like Rancher, which is a Kubernetes cluster management tool in their local certificate authority kind of a project. So, but interestingly, over 95% of these resolvers actually claim to be authoritative in their answers and set the AA bit in the response that we received. But 25% of them set the AD bit and claiming to have validated DNSSEC responses. And this is especially strange given that the resolver's IP addresses, again, do not actually belong, one, to Google's advertised IP ranges, so they're not the name servers that we're speaking to, but also the fact that Google doesn't sign its zones using DNSSEC. But we also observed the longitudinal data from 101 days and observed that over 35% of these resolvers that we find every day typically tend to be misconfigured. And this chart shows the distribution, shows how over time we also see an increase in the number of open DNS resolvers and also increase in the misconfigurations that are out there. So there's a little bit of a trend over here. Another thing we observed was that DNS resolvers are actually extremely transient on today's internet, and only 2.1% of the resolvers, the resolver IP addresses that we see on the first day of the scan actually are maintained until the 100th day of the scan. And the teal line over here kind of shows the decay, and the pink line shows the cumulative growth over the 100 days. And this is particularly really interesting because this means that there are resolvers that are being spun up temporarily, maybe because being configured to be public initially when they're set up, but later may be fixed and made private. But also we notice this bimodal distribution where there is a small 1% number of resolvers that actually have very long service uptimes at the same IP addresses that we've seen them for all these 100 days. So we added another query to the mix, and we started working with a broken DNSSEC.net, which is a well-known zone that contains a broken DNSSEC signature, and these should not actually validate the entire DNSSEC chain. And when we made these queries, we would have ideally expected that resolvers which are validating send us an appropriate error code and actually do not respond with the IP address, which is a Cloudflare IP address that we would expect to see. But what we observed was pretty surprising. And even though we had a much smaller number of resolvers that actually responded to this query, 92% of these actually did answer with the correct IP addresses, and when in fact we should have expected an error message. So these resolvers are not really validating resolvers at this point, and they might pose a significant risk to the clients who rely on their services. So, but also the split between the lack of incorrect responses over here compared to the number of IP addresses in the answers that were incorrect for Google.com queries seem to indicate that either the queries for Google.com are treated specially, or it could just be an artifact of reaching a bunch of machines that have censorship attempts over there. But overall, what we do notice is that there is a growing deployment of these DNS resolvers to comply with local regulations. And eventually, these resolvers becoming in-network services makes it really hard for external scanning-based mechanisms like what we did here to work in the future. So, but also the transient nature of these DNS resolvers that we notice also makes it harder to kind of study their behavior over time, or study what the intent of these resolvers are and why they exist and things like that. But throwing in the additional possibility for on-path middle boxes to actually tamper these responses, I think it makes an interesting future research effort. But a lot of the clients today actually do not use the DNSSEC bit in their queries, and they rely on using a trusted, validating recursive resolver. But is it time for us today, for the clients to actually enable this bit and send their queries by setting this bit? So thank you so much. I'm open to any questions. I see two of them in the queue.
Yes, and again, we'll close the queue in a few seconds. Go ahead.
Okay. Hi, Maynard from TU Dresden. Can you go back to slide 6, please?
Yes.
I can already start with my question. Or it's just something I want to point out, because you said you were a bit surprised about why Shadow Server identifies 2.5 million open resolvers, and you see such a lot of more open resolvers. I think that's due to the scanning setup, and I'm pretty sure because we also see around about 10 million resolvers, but we have some restrictions. We want to filter out some responses. So in the end, we also come up with 2.5 million devices.
Okay, thank you. Yeah.
Jeff Houston, you borrowed a slide from APNIC, but actually it comes to a really important kind of issue around this area of measurement. That is not a measure of resolvers. That's a measure of end users and the resolvers that they use. So in this case, we're talking about the behavior of end clients and effectively which recursive resolvers receive those queries and then send them off to authoritatives. And then you leap immediately into a different world. I scan IP addresses, I find things that look like resolvers, and I analyze their behavior. And I suppose the really big question is, are there any end users behind any of those resolvers that you find, or is this an aberrant piece of noise that pops up that talks on UDP port 53, but is never seen in any other context? And so it's hard to actually understand the import of what you're concluding in the rest of this pack without truly understanding the extent to which you're looking at random noise, or you're looking at systematic behavior inside operational networks that end users rely on. And one of the things you might want to think about is correlating those IP addresses you find against known lists of known resolvers with known clients behind it to understand whether there's any commonality at all, or whether you just spend a whole lot of time analyzing noise. Thank you.
Yeah, thank you. I fully agree with that. I think that's one of the biggest concerns that we had is we find a lot of these resolvers, but are these even do they even have clients behind them? And if they do, then there's a risk, but we don't know if they have clients behind them. So I fully agree with you. Thank you.
Thank you. And we just go on for the next presentation. Right on. We cannot hear you yet. You're muted still.
It's working right now.
Yes,
right?
much better. Thank you. Go ahead.
Yeah, so hi everyone, I'm Weiton, and let's talk about measuring the RV in RPKI. So this is a joint work with Virginia Tech, UC Berkeley, RIPE, IJ, and ISO. So RPKI is a protocol to secure BDP. So let's first talk about BDP. The BDP is an internet routing protocol, and it works based on announcements to build a path to origin. But there is no security feature built in, so theoretically, anyone participating in BDP protocol can announce any other's IP space. And there are a lot of real-world BDP hijacks that cause whether service outage or millions of dollars lost. So due to this issue, there are many secure BDP protocols introduced, and RPKI is the most recent one. It is first introduced in 2008, and recently more than 40% of ISP spaces are verifiable with RPKI. So how RPKI works? Firstly, resource owners can create a certificate contains AES numbers and IP perfect they owned, which is called ROA, and this ROA will be signed by its LIR or directly IRs and stored in a public repositories. And other networks can fetch all ROAs from public repositories and create a perfect to AES mapping database. If a router receives an BGP announcement contains IP perfect and AES paths, it will take the perfect and origin AES numbers to see if it is in the mapping table. If it is matched, it means that origin is authorized to announce such BGP announcement, which we call RPKI valid, and that routers can accept announcement. On the contrary, if the perfect is announced by another AES that is not authorized, the routers will find out and will label this announcement as RPK invalid and filter it. This validation and filtering process is called a root origin validation, which is RV. So in order to understand how RPKI is deployed today, we need to answer two questions. The first is how many network creates ROA, and the second is how many network deploy RV. So the first question is rather straightforward, and you can find measurement result in our IMC 19th paper. But the second question is more challenging, since we can't go to every network operators and ask them how they set up their routers. So there are many successful works trying to solve these questions, measuring the RV deployment. They usually announce their own experiment perfect and use vantage point from some platform to collect data, like root views for control plane experiment or RIPE LLS for data plane. But due to the small number of vantage points, these methodologies are limited on coverage. So there are some attempts to extend coverage like Ethnic. They use Google Ad Network. So what they did is ask their vantage point in Google Ad Network to send HTTP requests to two URL. One is under valid perfect and other is under invalid perfect. However, they only use one invalid perfect, but ROA is not all or nothing case. For example, some ASs may not filter invalid announcement coming from the customer, so this measurement will be easily impacted. So to make one step further, we want more vantage point to cover more ASs, and we want more RPK invalid perfect to make the measurement robust. So we present a new method, which is called Vista, that can overcome these two challenges. For the first one, Vista used in the world invalid perfect to run measurement. For the second one, we use a technique called IP side channel. For the first challenge, using invalid perfect for the measurements, it will be pretty hard to actually obtain many perfect, and it's also not a good idea to wasting IPv4 resources. So our solution is, how about use the invalid perfect in the world? The question is, are there so many invalid perfect we can use? So we collect BGP tables from root views and validate them with ROAs. These two figures shows the result over 2 years. As you can see in the top figure right now, more than 40% of perfect are covered in ROA, and the bottom figure shows that more than 0.7% of them are RPK invalid. So there are actually plenty of perfects that we can use. So now we solved the first challenge. The remaining challenge is how to collect more vantage point. So we use a technique called IP-ID side channel, which allow us to infer the connectivity between two hosts of the path, which means that if we want to infer the connectivity between the A and B without directly control whether A or B. So how this IP-ID side channel works? Firstly, IP-ID is a field in IP header. It's originally designed to assist package fragmentation by assigning a unique identifier for each package. Different systems have different ways to assign IP-ID for each IP package. Some OS will use a global counter, which means IP-ID will increase 1 whenever it sends a new package, regardless of the destination IP address. So how can we use IP-ID to infer the connectivity? Now we have hosts on the invalid perfect that can respond to the TCP handshake, which we call target, and another host that have global counter, which we call reflectors. We first send SYN package to reflectors, and the reflectors will send back SYN ACK package, which contains IP-ID in the header. So we know the current value of the counters. Then we send a SYN package to target with spoofing source IP address of reflectors. The target will send ACK to the reflector, and the reflector will send back reset, make the IP-ID increase 1. Then we send a SYN packet again to record IP-ID. So now we know how IP-ID side channel works, so we can use this to infer the connectivities. There are 3 scenarios. First is no filtering, which means the traffic they happily going through target to reflectors. The second is inbound filtering, which means the traffic from target cannot reach the reflectors. And then we have mostly the ROA cases, which is outbound filtering, which means the reflectors cannot reach the target. So how can we distinguish these 3 scenarios in IP-ID? So for example, we send a 10 spoof SYN package at the same time and want to see whether there's a spike in the IP-ID growth rate. If there's no filtering, we can see 1 spike when the reflector send reset to target. If there is inbound filtering, which is the middle figure, we can't see any spike because there's no traffic arrive. So if there's outbound filtering, which is the right figure, we also can find a spike when the packet arrives. But the thing is that since the target can't get a reset package, it will retransmit a packet again, so there will be multiple spikes. So in that way, we can distinguish 3 scenarios. So now we have plenty of invalid perfect in the world, and we can obtain many vantage points using IP-ID side channel. But there's still one step, which is how can we measure our way from the connectivity between invalid perfect and vantage point. So we introduce our score, which is the percentage of target that all reflectors on that AS cannot reach to. 100% means that AS cannot reach to any invalid perfect, and 0% means it can reach to all of them. However, the always score is not perfectly matching with always deployment. If we find one AS with 100% always score, it does not directly means that AS is deploying always itself, but maybe also because all upstreams of that AS are doing always. But this always score can still be used to understand how the internet is protected under always. So we run our Vista from December 2021 and keep it running till today. Right now, our Vista have covered more than 28K ASCs in more than 200 countries. To cross-validate our result, we manually collect our status through personal communications, posts from the network operators, and we also do a survey with manners participants. So we only find 3 inconsistency, and we have proved that at least 1 inconsistent AS is because of an out-of-date post. Then we want to see how many networks are fully protected with RV nowadays. So this figure is the percentage of ASs always defined with 100% RV score for each day, which means when the point on these ASs cannot reach to any invalid perfect. As we can see, it is increasing from 6% to 12% over the last 2 years, but 12% is still not enough to secure the entire internet. The good news is we found large networks are more likely to deploy RV, and right now 16 of 17 tier 1 ASs are with very high RV score. Since they are tier 1 and do not have upstreams, we believe they have deployed RV. So why large networks are more important? Because deploying RV will not only protect networks themselves, but also provide a benefit to their customer peers through impasse filtering. Using our Vista, we found some real-world examples. This figure shows our score of KPN and its 6 customers. KPN's blue line is a large ISP that we find to deploy RV on March 2022. Our Vista captured 6 customers of KPN, and 4 of them also jumped to 100% RV score. And we also find some cross-damage cases where one AS deploy RV, but is still vulnerable because of its upstreams not deploying RV. So for conclusion, we present our Vista, a platform to measure the protection of RV. And with 2 years running, we successfully measured our status of more than 28,000 ASs. So we publish all this data and source code in here, and we point out there's a need of future study to distinguish RV deployment and RV protection in a very large scale. Thanks a lot, and I'm willing to take any questions.
Thank you so much. Very nice study. We actually do have 2 minutes for questions. Okay, that gives us more time for questions for the other talks. Thank you so much, Weitong.
Thank you.
And we move on. Maxime, you're in the room, aren't you? Yes, there you are. Do you want to request sharing? Now you have to select.
Okay. So hello, I'm Maxime. I'm going to present joint work with Olivier Bonaventure. So this talk is based on an article we did together. We're going to reach to it, but we're going to start first with a simple question. So I'm living in Belgium, and I'm subscribed to a DSL line to get internet. And today, latency is becoming more important, and I'm looking into improving my latency, my end-to-end latency from my home to Google. And the question I'm asking myself is, fiber is getting available in Belgium finally. Should I switch to it? So what does impact end-to-end latency? So there is the home network. I'm connected to Ethernet. There is the access network. That was my question. But there is also the peerings of the ISPs themselves. So let's look from this simple 3-panel view. And actually, is all those elements just the only things at play? Isn't also address family coming into play? There are several areas where it could affect the end-to-end latency. So in the early days of V6 deployment, the access networks itself could be different. But what is most plausible today is that the peerings using V4 and V6 are largely different. The peerings from the ISP to the service providers and the general internet could vary from V6 and V4. So today I'm using V6, because I'm using modern applications and hosts favor IPv6 using IPable. So we could supplement this kind of, the question is getting funny, but now the question becomes, should I switch to fiber or use IPv4? And then what will bring the most difference is changing the access technology, or kind of using different peerings will bring the most results. To answer the question, I use RIPE Atlas and then run queries from the probes connected to my ISP network. And here are the results for V6. I took the 10 most fastest results. It seems like the 5 first probes are connected to fiber because they have a lower RTT. They're all kind of in the same range. And then the 5 lower ones are connected to DSL. Now let's look at V4 and keep the V6 results in gray to compare. Here it seems that changing the address family does also improve latency, and by quite a bit. So where does this address family end-to-end latency come from? To answer the question, I ran some trace routes as well from the probes. And if we look at the results first, we're looking at the trace route at a very peculiar point, just as it exits my ISP network and enters Google. And if we look at the density of the trace route RDDs, we see that in IPv4 there is a slight increment in RTT, but not that much. If we look at the results in V6, it becomes apparent that the problem was they're pairing together. It's causing this difference in RTT. So now okay, that was a small anecdote. Let's ask smart question now. So is this common in the internet today? Is there one that is always better than the other? Or are these differences spread? Are they common to the source? Do they depend on the destinations? And do they change over time? So to answer this question again, I use RIPE Atlas, and I use all the data that is available in RIPE Atlas from the 10,000 probes towards all the anchors. So anchors are single machines that are well connected throughout the world. And they do HTTP tests over, they do a simple GET request and response over HTTP, over V4 and V6, kind of at the same times and periodically throughout the day. So if I take all the measurements, and I get a lot of them just looking at the first week of June, and then compute the ratios between V4 and V6 request compilation time, and plot the CDF, we see that it has a S shape. It is quite centered, so no address family as a global advantage. The one thing that we can note is that there is a significant difference in some cases. Let's look more into those differences. I've taken all the measurements as a whole, but now let's look per source and destination. Let's isolate per probe and anchors, and we have a lot of them in our data. And all of them have roughly more than 300 HTTP tests, because over a week they do test every 30 minutes. And let's try to classify the differences in request completion time between IPv4 and IPv6. And I performed some statistical tests to try to categorize them, and found out that actually there are 3 categories. IPv4 is best, meaning lower request completion time. IPv6 is best, or none is strongly better, as per my statistical test. And actually the categories are quite well spread. There is a good chance that you will fall into one of the 3. But are those results stable over time? And from a given probe, like from my home, is always one better than the other? Should I just disable the bad one? To look into the first question, the stability over time, we did some change point analysis on the request completion time over time, and then redid the statistical test on each segment. We took segments of at least 30 points, so that covers 10, 15 hours in the day, and found out that there is a difference between the whole classification for a week and then some segments of the request completion time that got classified differently. And so the differences are mostly stable, because consistent is the greatest category, but there is a significant dynamicity. Sometimes you get better latency with one address family, but then it changes during the day. It can changes to none is better, but it can also flip. Regarding the other questions, whether it was common to the source, no, you just can't, it's not shown on the slide, but you can't just disable one. If you do that, you cannot reach all destinations, I mean, all anchors of RIPE with the lowest latency. So at this point, I want to emphasize that those latency differences are real, at least from the vantage of RIPE Atlas, which is quite a big vantage point. And sometimes they play in favor of IPv6, but sometimes they don't. And so in this day and age of rising importance of latency and IPv6 transition, it is very important to test IPv6 for latency as well, and to improve how latency is behaving, how IPv6 is behaving in terms of latency. If you want to improve things now, there's also something that we're looking into our research article, which is finding a new way to select the address family and using the lessons that we learned from our RAP analysis. I'm just going to go over rapidly what the questions that we are looking into the article. So we are looking at two questions, knowing that the differences happen most in the after the user network. We're asking ourselves how to steer hosts, and we're taking this operating point where we're looking at how the DNS resolver running in the, being the boundary between the user network and the WAN could help, because it is also the boundary between domain names and IP address, and eventually IP address family. So you all know that IPv4 prefers IPv6. There is IPv4 version 3 now that is using HTTPS records. And what we could do is, when we know that one is better than the other, we could give priority using HTTPS records. For experiments, what we did is just use mapped addresses. It is for experiment. It prevents the fallback, but it is good for experiment. Then the next question we looked into the article is how to select the best family, and we formulated this as a problem balancing exploration and exploitation, and this is classical of reinforcement learning problems. There is more to read in the paper if you're interested into this kind of research work, and I'm going to jump into the conclusion to let some room for questions, if any. So we're interested more than just this v4, v6 problem. We're more interested also in IPv6 multi-homing, because when you have multiple IPv6 provider, it is expected that one can reach one destination faster than the other, but not in all cases, not depending on the destination, for instance. And so this kind of techniques could also apply there. I guess that's it, yeah.
Perfect. First question.
Hi, I'm Simon Leinen from Switch. Thanks for the talk. My first reaction to this slide 18, where the RTT changes on the first traceroute hop in the peer network, in the Google's network, is that the return path must be different, because even the lowest RTT in the right beige graph is much higher than for IPv4. So I would assume that IPv6 traffic is routed along a different path back to you.
Okay.
So, but of course, this is just a minor detail, but
Interesting.
I think it warrants some thought, because the aggregation is different in IPv6 versus IPv4, and thus the possibilities of doing traffic engineering are probably different. From my experience as an operator, the topology is not very different. We have exactly the same path to Google or all the other peers over IPv4 and IPv6. That may have been a difference maybe 10 years ago, but today I think it's largely congruent. But there may be other differences hidden here, related to routing practices. So that's maybe an interesting avenue for research. And also, I think your observations are a good argument for doing multipath, but probably you know that already. Thanks a lot.
Thank you for the comments.
Tommy.
Hi, Tommy Pauly from Apple. Just wanted to say thank you for doing this work. I think it's interesting to see yet like another way to look at these numbers. Out of curiosity, I was just kind of running some of the metrics we see now for v4, v6, and they're very close, but still, v6 globally does seem to be faster. I think we've shared some of these numbers
Hmm.
before, particularly at the P90 levels. And one of the things we found before also is v6 support correlates highly to other better things in your network, like other more modern protocol stacks, and that can certainly bias things.
Hmm.
So I think overall the numbers, in your story of what should we choose for our stack, like let's still do v6 because in general it's getting you onto a better version of the internet. But I also wanted to point out for the Happy Eyeballs work, as you mentioned for v3, I think it's really interesting what you're bringing up around priority and how the use of priority can allow us to potentially indicate the quirks of which works better or not. And the incorporation of priority into the algorithm is still in flux. And so I'd love to see some of this data and some of these experiments fold back into that work. So I encourage you to write to the list or file issues to help guide that work.
Thank you.
And that's the IPv, the v6 ops list, right? You're talking about.
Yes.
It's not adopted yet, but yes, it's the work we're discussing in v6 ops.
And Tommy, just bring some measurements next time here.
Yeah, I should. We haven't refreshed our measurements in a while. Yeah.
All right, Eric Kinnear, also from Apple. Clearly, we think this is cool and care about it.
Cool.
Thank you for doing this. This is really interesting to see. And I think one of the things that is really cool here that we don't have in the data from what we're seeing in the wild, as it were, is that in our data, we're not doing an A-B comparison for exactly that same route. And so part of what we're seeing is that in cases where V6 wins the Happy Eyeballs race, those situations tend to result in faster, lower latency, faster HTTP requests. And we see that is consistent across HTTP and just, like the RTT estimate from TCP and Quick. So maybe that is a statement that Happy Eyeballs is helping and or working in that the thing that we see being preferred tends to be faster. But faster here is not faster for if we did exactly the same route.
Exactly.
It's really the rate at which we see V6 winning that race that tells us whether or not we think V6 versus V4 would have been faster.
Exactly. Also, the timer for racing could be, it's larger than the delays I'm looking during the study. So I'm looking at smaller improvements that get past this timer.
Yeah, and we will only put V4 in front of V6 if it's more than somewhere in the tens of milliseconds faster based on historical data too. So if you're seeing a very small delta, we'll still try to stick with V6 for non-latency reasons.
Okay, thank you for all the comments. Thank you.
Yeah, I think there's more things to talk offline. Thank you so much for your talk. And we continue with IPv6.
Okay. Yeah, welcome. My name is Johannes, and I'm here today as a maintainer of the IPv6 hit list. Currently, this is shared work of the Technical University of Munich with the Max Planck Institute of Informatics. What is a hit list? Why do we need it? Well, basically, the IPv6 address space is infeasible to scan. It's way too large. It's sparsely used only. So to cover it in research as well, we need to find other solutions. And a common approach here is to create hit lists with interesting and responsive addresses. One of the major hit lists here was established by Oliver Gasser in 2018. The main idea, it's a cumulative hit list collecting addresses from different sources. So for example, DNS resolutions or trace routes. It applies some filters for ethical reasons, and afterwards it probes them on a regular basis for different protocols such as ICMP, TCP on different ports, and UDP, and it publishes those results on a regular basis for others to use. So you can apply to this service and use the data for your IPv6 measurements as well. We still maintain this, and we updated this in 2 steps, one published at IMC last year and one published at TMA this year. And we asked us several questions. First, what is the current status? How did it develop? Second, are alias prefixes, so-called alias prefixes, still relevant or still a problem? What they are, I will talk about in a future slide. And at the end, can we improve the service to make better use of it in the future? Now, let's talk about the history. And some results here also apply to the DNS stuff from Sudesh. There are some similarities here. In the beginning, Oliver Gasser collected roughly 90 million addresses. In 2022, we had seen at least 800 million addresses once. 250 million out of those are filtered as they are aliased. 405 million are filtered as they were not responsive for at least 30 days. So afterwards, we reduce the load on the network and try to improve our scans. However, we see that up to 100 million addresses were responsive at the end. But if we look at the distribution across protocols, we see that most of them were responsive to DNS at the end, so UDP port 53 probes. And in comparison, ICMP, only 3 million addresses were responsive. So we wanted to look into that, why that is the case. And at the end, actually, we found those are injections and no real answers. So we probed for DNS with a query for www.google.com. We received more than one answer for most of them. All the addresses were invalid. In our case, Teredo addresses, definitely not used by Google. If we checked another domain, we saw no responses. If we checked a domain under our control, we saw no query at our name servers. And yeah, all of them came from autonomous systems within China. So crossing the border there at the network somehow triggered those injections. No real answers seen here. So what we did is we filtered all of them. We cleaned the hit list. We cleaned the historic data. So all historic data is clean by now and can be used again. And what we see a steady development of the service. There is a small increase. It's not that easily visible with the logarithmic y-axis here. But at the end, ICMP is the most responsive protocol with roughly 3 million addresses in 2022, followed by the TCP protocols and then UDP 53 and UDP 443. Next question was basically, why is UDP 443 so bad here? Why didn't QUIC pick up more? And this is mostly due to those alias prefixes that are filtered. The idea here is that the IPv6 address space is definitely large enough. A single host can use a complete prefix as an alias for himself or itself. So a single host can use all addresses within that prefix and just respond to them. This is visible, this is definitely the case, and a single such prefix, even if it's only a /64, is infeasible to scan and would induce large biases. To filter them, different suggestions in the past were to, well, you can simply generate 16 random addresses within a prefix, and that all of them are responsive is highly unlikely. So just generate 16 random addresses, they should not respond in theory, not all of them. This is done by the service and all those prefixes are filtered. But when we look at them in more detail, well, we find a lot of them are actually announced by CDNs at the end. So we saw that 98% of the address space Fastly announces in IPv6 is filtered by us. All of them are responsive to some degree in this case and are filtered. We also see that a lot of domains resolve to those addresses or to those prefixes. So for Cloudflare, it's similar. 10 million domains are within or hosted within those alias prefixes. And on the other side, we did some fingerprinting there to check whether it's a single host or multiple hosts. What we found is it's not a single host, but at the end, it's also not a one-to-one mapping. So we don't find a single host behind each address. There is some sort of load balancing. There is some other stuff happening here. Still, all of them are responsive. You can create a hit list with multiple billion responsive addresses. Just taking the address space of Fastly or Cloudflare is not relevant, I guess. And we still filter it in the hit list. But at the end, we suggest that you use addresses out of those alias prefixes or fully responsive prefixes in your studies when you want to cover IPv6 as well. We published a list of those address prefixes on a regular basis as well. You can use them, include CDNs there as well. Finally, we wanted to extend the hit list, and we did two things here. One is relatively simple. We added category information based on PeeringDB, a community-maintained database where everybody can add some sort of category to their autonomous system. We add this information. You can filter the hit list now based on targets you're interested in if you have this desire. Most of the hit list is categorized as content, ISP, or NSP, what should be expected here. But there are some out of educational or non-profit categories as well. You can use that. It's also available for the historic data. And finally, we set out to extend the hit list. So only 3 million addresses were responsive. There were way more addresses responsive for IPv4. how can we improve this? And one common idea here is to apply target generation algorithms. And the idea is that addresses are assigned with a specific policy or idea in mind, and not randomly assigned in most of the cases. And if this policy can be learned, we can guess or generate new addresses and test them afterwards. There are a lot of those out there. We tested them in 2 steps, in the first and in the second study, with different inputs and different configurations. Just some examples of 4 algorithms here. They generate highly different amount of addresses. So given 3 million addresses at the beginning, 6graph generated 125 candidates, and actually 3.8 million were responsive. So those were new addresses we could add. Others, like 6vec-LM, only generated 70,000 addresses, but still some are responsive. So over 2 runs, we generated a lot of addresses. A lot of them are only responsive for a short amount of time, random guesses, not usable, but we added everything to the hit list, and by now it looks like this. The service is out there. We added new addresses. We removed all those injections. You see at the F in the figure below, that was the first study in 2022. We added new addresses, and then in 23, new addresses again. As I said, not all are still responsive, but we are now at 9 million responsive addresses you can use for your study. If you have any ideas or any input for us, we're happy to talk about that. Are there questions?
There are none, and we don't have time. But thank you so much for bringing your work and doing the work for the community, and you can talk to Johannes afterwards. So the last presentation will be an online presentation and will be about trackers, which is actually quite relevant to current work in the IETF.
Okay, great. Hello, everyone. My name is Yasser Zeki. This is sort of a joined work that we did with Matteo Vervello from Nokia Bell Labs in assessing and measuring the tag's performance basically in the wild. So for those of you who do not know how these tags work, these tags are like simple devices. They're meant basically to locate lost items, and they work opportunistically in the sense that they send Bluetooth beacons, and if they rely on sort of on bystanders. If there's like a person passing by one of these tags and have a phone that is capable of reporting these the tag location, will listen to the beacon and then will report the GPS location of the phone to either Apple or Samsung servers, and then the owner would be notified by the location of the tag. The ecosystem differs a little bit in the sense that, for example, for Apple, it's a default sort of reporting. You cannot disable this thing. If your iPhone passes by and find an AirTag, it will report the location. On the other hand, for Samsung, it's only for Galaxy phones, and it's opt-in. So by default, many devices do not report the location of the tags. And that kind of already creates sort of discrepancy between the number of reporting devices in the wild. So recently, there's been a lot of news about these location tags being used for sort of, or being misused for stalking. And we were curious basically to understand what is the accuracy of these tags in the wild and whether they really could be used for stalking. As a result, we basically, our experimental sort of setup was, we had a vantage point that consisted of a Xiaomi Redmi phone, which was not reporting neither of the tags, neither the smart tag or the Apple AirTag. But we used this, the sort of true GPS location of the phone. It was recording the GPS location of the phone in all time. And then we had a 3D printed cover for that phone where we mounted these 2 tags, the Apple AirTag and the Samsung AirTag. And then we collected, basically we built crawlers for Find My and SmartThings. These are the apps that both Apple and Samsung uses to allow the owner to see the location of the tags. We built crawlers to store the location, the GPS locations of these tags. And we were able to compare basically to the ground truth that the phone was reporting. How do we measure accuracy? We say we kind of vary 2 different things. We say that a tag is sort of discoverable if it's within a particular radius of the ground truth, and we vary this radius. And we also look at the time. So how much time does it take until a tag will become discoverable in the correct location? So there are 2 always elements that we look. one is time, and the other one is the radius from the true location. Our experiment basically spanned 6 different countries with 20 cities. It was about 2 months, and we had about 24,000 different location reports in total. And we excluded home locations because home locations are very sort of peculiar. It's mainly stationary. There's a lot of devices that could report. So we wanted really to remove that in order not to bias or screw our results. Here, I'm going to show you the accuracy of these smart tags. On the left side, you see over a 10-meter radius. Blue, you see the Apple accuracy, and in orange, you see the Samsung accuracy. And we're also sort of interested in seeing the combined effect, because what if somebody uses both tags to basically increase the accuracy of stalking, to basically being able to pinpoint exactly where the location of the victim is. And as you can see, it kind of flats out in about 60% accuracy. So 60% of the times, you're able to find the location of the victim at least after 2 hours. If you relax basically the condition and you go to 100 meters, which is the figure on the left, we're able to increase, you're able to see like an accuracy of about 70%. What's interesting is the combined effect is not really sort of an addition of the two. There's about 10 or 15% addition in terms of like accuracy, but it's not really a combination of like adding the two. Additionally, we're also curious to see like different effects of mobility, day of time, day of the week. And I'm going to go very quickly over this because I don't have that much time. But what you can see basically with stationary and pedestrian, these are like the ways where you can get higher accuracy. And then the more you start sort of in terms of like bigger transit, whether it's jogging or in a car or in public transportation, the accuracy basically goes down. There's not that big of a difference over the day of the time or the weekend versus sort of weekday in general. We were also curious to see like basically what's the effect of the population density. So we used Uber hexagonal hierarchical spatial index to segment the location. This was one of the locations that we used, which was in Abu Dhabi, where we located, and you see these hexagonal things. And then we use the contour population density data set to get an estimate of the population size, because in reality, in the wild, there is no way of knowing how many devices are there. And the hypothesis there is that you can kind of correlate the population density with how many devices that are capable of reporting. And you can see here on the left side, when you have a low density area, there is a high chance, 25% of the cases, where you're not going to be able to get any accuracy. You have about a 0% sort of recording of discovering where the location is. And this kind of drops down in the medium density and the high density to something that is a lot lower in general between sort of these density locations. Now, given that we don't really know the ground truth of the devices that we have, we wanted to set sort of a controlled experiment that we know exactly how many reporting devices are there. And we set up an experiment in the cafeteria at the university. We had our vantage point in a high flux area, which is at the cashier, because all the students have to go to the cashier to pay for their meals. And then we sort of, with the help of our IT department, we were able to get estimates exactly on the number of Apple and Samsung devices in the cafeteria throughout the day. And here were the results, which was kind of interesting. The bar graph shows you the number of devices. Blue and Apple devices, and orange are the Samsung devices. And as you can see, we had about 6 times higher number of Apple devices in the cafeteria versus the Samsung. However, what's interesting is the update rates of these tags, the AirTag and the Smart Tag. Both of them were able to get about 15 updates per hour, regardless of the number of devices that you see here. I mean, Samsung was able to kind of keep up neck and neck with Apple in terms of the update rates compared to, despite the fact that there's a lot less number of users. And here we bucketize things as well in terms of like histogram of how many devices and binning them. And you see the same thing. Samsung has a lot aggressive update rate compared to Apple. And that could explain as well why in the accuracy figures that we saw earlier, both of them have like very similar accuracy numbers. So we were curious why this is sort of the case. And we measured basically the signal strength versus the distance. Here on the left side, you can see the AirTag numbers at different distances from 0, 10, and 20 meters. And on the right, you have the smart tag, which is the Samsung one. And what this figure shows you is that Samsung is a lot more aggressive in terms of like sending higher beacon power. And they send also these beacons more frequently, realizing that they have less amount of devices around that could report. And as such, that's why kind of it's able to keep up with the Apple AirTag sort of performance. However, this comes at an expense of the power of the battery lifetime between Apple and Samsung. So in conclusion, these tags could sort of provide good, accurate measure in general and within like a kind of like an hour or 2 hour period, but it's still kind of far from being able to like stalk a person to like a high resolution sort of accuracy. And more research is of course needed to study basically what should be used to combat the misuses of this. We are repeating the experiment this year again towards the end of the year by adding more tags like the tile as well. And we're doing this with the Amigo sort of framework that we've built, where we have 5G capable phones. So if anyone is interested in sort of doing some measurements in the wild with like multiple devices across the globe, please reach out to us and we're happy to kind of incorporate this as well. Right, that's it. I know that I'm on time, but if there are any questions, I'm happy to answer, or even offline.
Yeah, thank you so much. Very interesting. And please bring back your updates next time very quickly. We don't have anybody in the queue and we're out of time. So please contact Yazir per email if you have any further questions. Thank you, everybody, especially to all the speakers, everybody who contributed, and also Brian Trammell taking notes. And see you next time.